Hey AP, this video is on periodicity. So periodicity is the behavior of elements and their properties across the periodic table in periods and down groups, which are columns. So periodicity states that elements in the same group have different outer electron configurations and therefore similar properties. And we're going to dive in to what that looks like in some very specific trends that happen across the periodic table. When we're looking at the periodic table, we can see that there are common ions based off of where electrons are in similar groups because of similar electron configurations. So we know that atoms want full or empty outer shells, which means they either want 8 electrons in their outer shell to have that octet or 0. So what they do is they're going to gain or lose valence electrons to do so that way they end up with a balanced outer shell, and that way they have all their electrons paired. So remember, our noble gases are considered inert, and that's because their electrons are all paired and they have a full outer shell. And then all of our atoms in between here, to the left of them, are either trying to gain or lose electrons to get towards that noble gas status. Now remember, we have our dividing line here, which divides our metals from our nonmetals. Okay, so these are, remember, our nonmetals. And remember, nonmetals want to gain electrons because it's easier for them to gain electrons to get to an octet. And then everybody else to the left are our metals. And metals are going to lose electrons. And they're going to lose electrons because they usually have valence electrons that are less than 4, and it's easier to lose less than 4 than to gain more than 4. The other thing to note is metals turn into positive ions, which we call cations. And then metals, because they gain electrons, they turn into negative ions called anions. And we've talked before about what ions they make based on where they are. But remember that anything in group 1 is going to have a positive 1 charge. It's going to lose their 1 valence electron. Group 2 are going to lose their 2 valence electrons. So it's going to go positive 2. Remember, our transition metals, they're going to vary. And that's why we write Roman numerals when we say their compound names. But these you could never say like, oh, it must be nickel 2. It would tell you that it's nickel 2 because it could be nickel 1, 2, or 3. Here, aluminum and gallium are going to be +3. Boron's technically a nonmetal, and that means that it could be -5, but we really don't use it that much. Carbon and silicon are going to go -4. Germanium underneath is +4. Then here, -3, because now we've switched, right, from metals to nonmetals. They're going to gain electrons to get to that noble gas notation. So nitrogen's going to gain 1, 2, 3 electrons to be more like neon. Oxygen's going to gain 2. Fluorine's going to gain 1. So that's where those charges come from. So we've talked about ionization a little bit. Ionization being the energy required to remove an electron from my atom to turn it into an ion. We can have our first ionization energy, which specifies the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to make 1 mole of gaseous ion. OUS. Ions. And we write that in a very specific way. So if I were ionizing magnesium, which would happen, right? Magnesium's a metal. It likes to get ionized. So 1, I'd have to turn it into a gas. So you heat it up to be really, really hot. And then what would happen is it would turn into an ion and remove an electron. And I need to show that these are gases here, and I need to show my number of electrons removed and that I've made an ion. AP College Board likes asking questions, especially on FRQs, where you write the reaction for the first ionization energy. So you can pretty much guarantee to expect to write this on your Unit 1 test. I could do my second ionization energy, which is the energy required to move yet another mole of electrons from 1 mole of gaseous ions to make 1 mole of gaseous +2 ions. Ignore my typo. And so here, now I'm removing yet another electron. So I have my magnesium plus 1, and now I'm turning into magnesium plus 2 because I'm removing another electron. Now, how much energy is required is going to depend on two parts. One, it all has to do with Coulomb's law, which is the attraction between our protons and our electrons, which we've been talking a lot about. We know that electrons are negative, protons are positive, and they're attracted to each other. Now, two things play into how much attraction there is in Coulomb's law. First is the nuclear charge. The things in the nucleus that have a charge are your protons. And so the number of protons is the nuclear charge. Remember that this is equal to the atomic number. So I can easily determine that based on the periodic table. And the other one is the shielding effect of the inner electrons. So if we were to think of a Bohr models have those shells. And the inside shells are going to shield the attraction of that nucleus from the outside shells. They get in the way. So the more electrons that are between the nucleus and the valence electrons, and the further away the electrons are, the smaller the attraction we're going to have between my nucleus, my nuclear charge, and my outermost electrons. So if my electrons are really far away, it's not going to require much energy to pull them off because they're hardly attracted to the nucleus. They're much closer, like when we looked at those core electrons in our PES spectra. Well, that requires a lot of energy to remove them because they're held really tightly. They have high attraction to the nucleus because they're so close to the nucleus. So let's take a look at a graph of this data. So this is a graph of first ionization energies of our first 20 elements. And we can see that we have this overall trend where we go up as we go across the period, and then we come back down as I go down to my next row of the periodic table, and then I climb, I hit the end, so number 10, this is neon, right? That's at the end of a row, and then I drop back down. After neon, this is sodium. So it drops back down. So if I look at, let's speed this up a little more. There we go. So I can see that hydrogen to helium, I've increased. That makes sense. I've increased my nuclear charge. I haven't changed any shielding. So therefore, these are held tighter because there's more nuclear charge. But then I drop down to lithium. Well, my ionization energy decreased a lot, right? And that's because now I have electrons in the next shell away from the nucleus. So now there's shielding happening. My 1s electrons are shielding my 2s1 electron. But now I'm adding to the same shell. So they're not getting further away. They're not increasing shielding because they're within the same shell. And my nuclear charge now is starting to creep up. And because they're at the same distance away, and I'm increasing my nuclear charge, well, now they're having more attraction. And we can see that here in our chart. So let's explain that. So across a period, my ionization energy increases because as the nuclear charge increases, my valence electrons would be trying to be removed from the same shell or energy level. And these are at the same distance from the nucleus. So as electrons are removed, this results in a higher charge to electron ratio and greater attraction between my nucleus and my valence electrons. So I'm increasing my charge, right? Atomic number is the same as my nuclear charge. I'm increasing my nuclear charge while adding electrons to the same shell. Therefore, they're going to get more attraction. All of a sudden, I add another shell. Now I'm moving down a group. Well, now it's going to decrease because now I've increased my shielding. I have inner shells that are preventing my outermost valence electrons from feeling any sort of attraction from the nucleus. So down a group decreases. Even though we gain nuclear charge, we also add new shells. Those shells are further away from the nucleus and are shielded from the attraction of the nucleus by inner shells of electrons. Okay, and shielding is another one of those vocabulary words that you're going to want to use along with Coulomb's law. Now, if I had one element and I started successively pulling off electrons, what would that chart look like? Well, we can understand that in a single element, it's going to be harder to continue to remove the next electron because the remaining electrons have reduced mutual repulsion, right? I know things that are like charge repel each other. So two electrons are going to repel each other because they're both negatively charged. If I have less of them around, they're going to start to get closer together because there's less pushing them apart, repelling them. Also, I'm then getting closer to the nucleus. And if I'm getting closer to the nucleus, I'm increasing my Coulombic attraction of my electrons to the nucleus. So if we were to look at ionization energies of sodium, again, this is in kilojoules per mole. So energy required to remove 1 mole of electrons. Sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. So we can see the energies, and this matches. So this is my 1s2, 2 electrons. Then I have my 2s, 2 electrons. And then the rest of these, 1, 2, 3, 4, 5, 6, are my 2p electrons and my 3s electrons. Is that right? That doesn't seem right. That's opposite. That is opposite. These are my core electrons over here. This is not like PES data. Ignore that. So we can see that to remove my first electron, this is my valence electron. Okay. So if this is my valence electrons, it does not require much energy at all to remove it. And this is my 3s1 electron. Not the 1s. This is my 3s1 electron. Whereas here, these are my 1s2 electrons. These are my core electrons on the inside innermost shell. And we can see that it is 141 and 159,000 kilojoules per mole. So we can see the huge difference between removing core electrons versus a valence electron. We can also see there's some pretty big jumps in energy. So from 496 to 400 or 4,000. So this we can see is a change in energy level or shell from the 3s to the 2. And then again, we can see another big change in a factor of 10. We go from 28,000 to 141,000. That again is another jump in energy levels because of that big factor of 10 of energy going from one shell to the next shell. So let's look at some ionization energies of two different elements, X and Y. Just lined up for you. So we can see that we have our information on element X. We have 3 pieces of information, and then Y, we have 6. So first question, what group is X likely to be found? Well, it looks like there's only 3 electrons that are able to be removed from X. So that means that it must be in the third group of the periodic table because it only has 3 valence electrons. So the other elements that only have 3 valence electrons is in groups 1, 2, 3. So it must be in this third group to have 3 valence electrons. Now, our element Y has 6 electrons that are able to be removed. So we can assume that it must be in the 6th group. 1, 2, 3, 4, 5, 6. So in oxygen's group here. Now, more than likely, we would see if this was an element that was further down the periodic table, we would see a lot more ionization energies that would increase really, really, really fast. For element X, we only have 3 ionization energies, so we can safely assume that this is probably, I think that's what it was asking. There are only 3, suggest reason, that there's only 3 valence electrons for this element. So because there are only 3 ionization energies listed for X, there must be only 3 valence electrons able to be removed. All right, so moving on to our next trend in the periodic table is atomic size. So atomic size is how big our elements are. As we move across a period, we are having an overall size decrease. And we know that helium and fluorine are some of our smallest elements. And we also know that down over here, right, down in this part of the periodic table, there's some of our biggest elements. Now, as we go across, our shielding stays constant because the same number of shells are present, right? There are 2 shells present in my entire second row. However, the nuclear charge increases 3, 4, 5, 6, 7, 8, 9, 10. And as my nuclear charge increases, but my elements are in this, or my electrons are in the same shell, that means that I'm increasing my Coulombic attraction of my nucleus to my outermost electrons, and I'm able to attract them in closer, so it gets smaller. Going down a group, although there is an increase in nuclear charge, electrons are adding in new shells further and further away from the nucleus. So I'm building out as I go down a group. And if I'm building out as I go down a group, that means that I'm getting bigger. And even though my nuclear charge is increasing, it can't handle how far away the electrons are in the further shells. So my size greatly increases and increases quickly moving down the periodic table. Now, what if I were to make ions? We talked a little bit about ions at the beginning, and we said a cation is where we lose electrons, and specifically, we lose valence electrons in the outermost shell. So that means that if I'm losing electrons in the outermost shell, it's going to get smaller because now my electrons aren't repelling each other as much. They're able to get closer. Also, my nuclear charge is staying the same, so that starts to become bigger in relation to my number of electrons, right? If I start with 10 and 10, and now my number of protons stays at 10, but my electron starts to decrease, that means that now I'm going to have way more of a positive charge, attracting less electrons, and it's going to be able to attract them in closer. So conversely, an anion is going to increase in size because it's gaining electrons. And it's gaining electrons in the outermost shell. As I add in more negative electrons to my outermost shell, they're going to continue to repel each other. And as they repel each other, they spread out. So that makes it bigger. So down a group increases, across a group decreases in terms of atoms. And then cations decrease because we're losing electrons in the outermost shell. Anions increase because we're gaining electrons in the outermost shell while we're keeping my nuclear charge the same. So if I wanted to arrange the following species, that's just a term for, we have atoms and ions here, in increasing size. Well, if I look at where they are on the periodic table, I have argon, potassium, calcium, sulfur, and chlorine. And these are ions as well. So first we can see that these are isoelectric. That's a word from the other day, meaning that they have the same number of electrons, right? They all have 18 electrons like argon. We know that argon's going to be in the middle because it is neutral. We know that our cations are small, so these are going to be smaller. And our anions are big. We know that as I lose electrons, I get smaller. So the more electrons lost, calcium lost more. This one's going to be the smallest. And as I gain electrons, I get bigger. So one that gained the most is going to be the biggest. So increasing size, calcium plus 2 is the smallest, then potassium, then argon, then chloride, and sulfide. All right, a couple more trends to talk about. One, electron affinity. Electron affinity is the opposite of electronegativity. So electron affinity is the energy change when electrons are added to an atom or ion, opposite of ionization energy, because that is when they are removed. And just like for ionization energies, we can write reactions, we can do the same thing for electron affinities. So the first electron affinity is the energy change when 1 mole of electrons is added to 1 mole of gaseous atoms to produce 1 mole of gaseous ions. Sounds familiar. Sounds like our ionization energies. And we can write that by my gaseous atom plus an electron makes a gaseous ion. I can make a second one by adding a second electron. So my gaseous ion plus an electron makes a gaseous ion with a -2 charge. So I can do the same things here. Now, as I go across a period, atoms continue to want to gain electrons to fill the outermost shell. So if I add electrons to the same shell, my overall size gets smaller, right? Because I'm moving to the right across the table. So I'm going to have more attraction from my nucleus to my outermost shell. And therefore, if I have more attraction, that means that it's going to want to continue to gain electrons. So my electron affinity increases. Now, if I go down a group, it's going to decrease. And it's going to decrease because now I'm adding to shells further away from the nucleus. Therefore, there's less Coulombic attraction. Less Coulombic attraction means that it doesn't really care about those outermost electrons. Take them or leave them. So it doesn't want to attract anymore. Are you starting to see the trend of Coulombic attraction playing a huge role in everything that happens here? Then we've got electronegativity. Again, something that we've talked about previously in chemistry. Electronegativity is the ability of an atom to attract an electron. As I go across the period, it increases. Again, the nucleus is going to attract electrons to achieve a full outer shell. Because the size of the atom decreases, thus greater Coulombic attraction to the valence electrons to fill, in our case, on the right-hand side, we have our p subshell. It's going to continue to fill it. And that's because of increased Coulombic attraction with electrons getting added to the same shell. If I'm going down a group, my size of the atom increases drastically because I'm adding shells to my atom. And those shells, every time I add them, I increase the amount of shielding of the nucleus. Therefore, there's less a Coulombic attraction. It essentially diminishes when I start to add too many shells. And my atom no longer wants to gain any more electrons. Finally, we can talk about properties. Across a period, properties can follow a trend. However, they usually peak at some point in the period and then decrease again. So they usually go kind of like up and then down, depending upon what the trend is, or down and then up. And this is usually because along a period, we switch between metals and nonmetals, and they have different physical properties. So we usually have something that comes up, and all of a sudden we've hit that dividing line, and then it goes back down because metals and nonmetals are opposite. However, within a group, they have the same number of valence electrons. And if they have the same number of valence electrons, that means that they're going to have similar properties because those electrons are the ones that do all of the chemical reactions and therefore going to behave similarly for physical reactions. Finally, we have chemical properties within a group. And luckily for us, they're going to follow the same trend as they do for physical properties. Again, because they have the same number of valence electrons, therefore they're going to behave similarly in a chemical process, and they're going to have just about the same properties. So lots of information. The way that you're going to get tested on this information is usually by explaining. So this is one where it's probably going to be an FRQ question, could be multiple choice, and you'll have to explain the trend that you see. So again, using vocabulary like shielding, Coulombic attraction, nuclear charge are going to be 3 key vocab words that they're going to look out for in your answers. And we'll practice tomorrow.